looks like you guys are well on track and have already set a solid foundation for this topic, the response of a state space equation. We'll be talking about, in general, the response of x star equals to ax plus bu, and we will talk about continuous time and discrete time cases. Let's start with the easy case. If I want to solve x star, if I want to solve a vector equation, x star equals ax plus bu, let's revisit what we can have for a scalar case, x dot equals ax plus bu, where these coefficients are all real and scalar. Here's the interesting observation that's key for this set of analysis. Imagine, think about what we are doing here. For this to work out, this function x, it must have the property, if you take the derivative of the function, it has the same, very similar structure as the original function itself. Right? What kind of function can have that property? Derivative is structurally the same as itself. Exponential function. Exponential function satisfies, taking the derivative of e at is aet dt. And then if it's negative, then you just have negative sign here. So derivative functions have this fantastic property. What else? What other functions? If you take the derivative, you sort of get something similar. Sine and cosine, right? So sine and cosine are also having the same property like this. Now, because of that, we can do some manipulations and then eventually obtain some solution. The way that, one way to do that is as follows. You recognize that this have the same structure, they are in the same family. So you shift the terms around, you combine them on the left-hand side, and then noting the property of exponential function, you sort of create this kind of structure. So you notice essentially d dt e negative at xt. You notice this one is going to give you, is chain rule, derivative e at x dot t plus chain rule, the derivative of this one, negative a e negative at xt. This is by experience and construction. You can see that this must be having some kind of exponential structures inside. Then you can solve the problem essentially quickly. On the left, you have the derivative of e negative at times x. On the right, you have some time functions e negative at times bu. That means the derivative d e negative at x equals this term times dt. And then just do integration. Integration, let's say from initial time t0 to terminal time t. Then integration of this one is e negative at xt minus the initial time, right? It's going to equal to integration of the right-hand side from t0 to t. So just to put these terms inside and claim, let's say the integration variable is tau, tau, tau. So that's how first order ordinary differential equation, the solution looks like. This formula is pretty handy. As you practice more, it's almost, it becomes some muscle memory in your mind. Any questions for this slide? All right. What we usually do is we start from 0. The initial time is usually 0. And in that case, we have, so in that case, we have e negative at xt equal to, if t0 is 0, then this becomes 1. And this x0 plus integration from 0 to t e negative 8 tau b u tau d tau. What we want in the end is x, right? So we want to be able to know how x looks like. So just multiply EAT on both sides and get from here to here. So you get the EAT and then EAT here. So you can combine terms. EAT times E negative A tau is EAT minus tau plus times BU tau. So that is the response to a first order ordinary differential equation with initial condition x0 and input u. So this is the free response. It depends only on the initial condition. And then this part is the forced response. It's the response after you apply an input, external input. All right, let's take a look at the free response. In all these cases, you see what is the most important term is the exponential function. It's going to define how the solution looks like. Let's take a look at the exponential function a little bit more carefully. So let's take a look at this one, the free response. Control engineers usually can tell very quickly once they are giving a problem, if they are giving a transfer function, usually they can quickly tell like how the response will look like. So if you apply a step signal to a control system, then experienced control engineers will tell like after how many seconds the system will go to some constant value. And that concept comes from here, time constant. It's talking about this. Let's say the system starts from some initial condition. And because the exponential function, the time response will look like, it's going to have different kind of shapes. If A is 0, then it's a constant. If A is positive, then it's exponentially increasing. And if A is negative, it's exponentially decaying. Right? So some typical numbers, if you plug in and use a calculator, you will know that if t is 1, so case 1, case 2, and case 3. If t is 1 times this constant, negative a, all right? So this is for the case a is negative. So if t is 1 over negative a, then you can see that the response is e a times 1 over negative a t a times x0, and it equals e negative 1 x0. So this value is about 37% of x0. So that means after this time, defined by 1 over negative a, the response goes to about 37%, somewhere here. Okay? So after this 1, we call 1 times time constant, it goes to here. A lot of signals has already decayed. And then if it's 3 times this special number, time constant, then you get E A 3 over negative AT, A times x0, so which is E negative 3 x0. Then this is a very small number. So E to the power of negative 3 is about 5%, so it's about right here. After 3 times this time constant, the signal is basically 0. You can regard the initial response, the free response, has died down. And after this, if you continue to increase time, then not a lot of significant changes. So if you go to 4 times this time constant is 2%, not a significant reduction compared to from here to here. So that's the time constant concept in this case. So A is a very important number. A will define how fast your system responds. If A is amazingly big, what does that mean? If A is negative 10 compared to negative 1, which system will be faster? Negative 10, right? The time response, the time constant is smaller. It means it takes less time to go down to 5% or 2%. All right, so that's the time constant, and that's the first order case. The general case, now you understand that, is very straightforward to obtain this one. It's the same structure. So it is also using the same concepts in the solution. The only difference in this case is now you have matrices. Now this is no longer scalar, but becomes a matrix here, and matrix here. But it has the same structure. Free response depend on initial condition. Forced response depend on U, the input. So the structure is entirely the same. And once we obtain, this is the complicated part. Once you get this, the output is easy. The output doesn't contain any derivatives. So output is just C times X plus D times U. Let's take a quick break. Let's finish up about responses, state space responses. So this is the formula. It's the same structure as the scalar case, but it's very different in how it's computed. Here is also important. The key elements are these exponential functions. So it's exponential function to the power of a matrix times a scalar time. The first question to ask is, what does this really mean? It's like exponential function, let's say A is 1, 1, 2, 2, and then times t minus t0. So what does this actually compute to? In the scalar case, it's so easy, but in this exponential case, it's different. First of all, what do you think? This is a matrix or a scalar? It is a matrix, right? Because somehow you got to make this work out. You have a EA t minus tau times B, right? So B is a matrix, B is a vector, or a matrix in general case. So you got to make this work somehow. So it's not a scalar anymore, and it's not as naive as we can imagine. It's not like it's not exponential function to all the individual elements. It's not that either. So it doesn't equal to t minus t0, t minus t0, 2t minus t0. It's not that. Okay? Doesn't equal to that as easy as that, but it involves some computations. And that is what we're going to clear up. All right. In the scalar case, since let's revisit the scalar case. So the way EAT is defined comes from the original definition or original property of exponential function of the scalar case. So the exponential function of a scalar case, this is actually a summation of infinite terms. So from Taylor expansion, this is exponential function. It equals 1 plus AT plus half of AT squared plus higher order terms about AT. This is from the Taylor expansion. All right. For this one, it has some special properties, right? This is a scalar. This is a scalar. These are all scalars. So for the matrix case, it's defined similarly. So just to replace little a with capital A, then you got the definition of exponential function to the power of a matrix term. So it's AT. So replaced one with a matrix, identity matrix, and then everything else with AT, capital AT. That's how this matrix is defined. A is a matrix, I is a matrix, so from here you can recognize it is a matrix. All right? So this is called a transition matrix for the system. It's transitioning, so this is called transition. It is transitioning from one initial state to another. And the time in this transition matrix is like the terminal time t minus the initial time t0. So it's transitioning from t0 to t. That's how it's defined. It has some interesting properties. So it satisfies this. If t is 0, if t is t0, meaning that I'm not going anywhere. I start at t0 and then the time it remains at t0. So this is transitioning to itself. EAT with t equal to t0 is identity. So if this is 0, this is identity. And this transition matrix equals identity. You're not transitioning to anywhere. And then if you are transitioning from, let's say, if you have consecutive transition, let's say you're transitioning from T1 to T2, and then from T2 to T3. All right? So it's going to be like this. So it's E A T3 minus T2 times E A T2 minus T1. So it's going to equal to, so this is from T1 to T2 and then to T3. It's going to equal to EA T3 minus T1. So you can compute, if only you want to know what is the transition state at T3, then you can kind of go over this intermediate state of transition. So that's this property. All right? So this is using the property of EAT1 times EAT2 equals EA with T1 plus T2. So transition, sequential transition can be simplified with from the beginning to the end. And then this is the inverse transitioning. So let's say you start from T1 and you transition to T2, you can go back from T2 to T1 by this inverse transition. It's like this. E A T2 minus T1 on the left-hand side, and then on the right-hand side is, if you think about E A T1 minus T2. This is transitioning from T2 to T1, and then you apply an inverse. It becomes reverse transition. So some general properties of the transition matrix. So there's one thing I want to remind you guys. When matrix becomes involved, sometimes it's very important to be careful about the computations. This one, it works out perfectly fine here. EAT1, EAT2 equals EAT1 plus T2. But in general, if you have EAT times EBT, in general, it doesn't equal to, you cannot just simply add up these two matrices and then get the result. This only works if AB and BA, they are the same. If these two matrix products, they are the same. All right? Let's put this into perspective by checking what this really means. So EAT, let's say, by this definition, it equals I plus AT plus half of AT squared, etc. dBT equals I BT BT squared, etc. So if you multiply them out, let's see what terms will appear. So if you do the product, you multiply out, you're going to get, so it's individual components, right? It's this multiplying this plus AT multiplying this. It's going to contain EAT, EBT contains I BT plus half of BT squared. This is the first component multiplication, plus AT multiplying IT, AT multiplying BT, so it's ABT squared plus half of AT BT squared, etc. So this will be sufficient to make my point. This is, by definition, how they should look like. Now, on the other hand, EA plus BT equals I ABT, just from the expansion, right? Treat this as a whole. T squared, and etc. All right. All right. So let's see. To make this equal to that, what can go wrong? Let's check term by term. We need an IN term, which is available from here. A plus BT is also available, right? I got AT, I got BT as well. Let's take a look at this term, this interesting term. So what do we need? This, it equals half of A plus B, A plus B. It equals half of, let's say, it's again, individual components multiply out. A squared plus AB, right? Plus BA plus B squared. So just component multiplication. Now, for this to equal to that, for EA plus BT to equal to this product, we need all these components to appear on this end. Do we have them all? I got half of I got half of B squared at least, right, from here. Half of B squared. And then I got half of A squared not coming up from here, but that actually wouldn't matter. Important thing is I need this to appear. Do you guys see? I need half of A times B and half of B times A to appear. And over here, what do I have? The only cross product term about A and B is in here, right? The only cross product of A and B is going to be this term times this term, right? This is half of AB t squared plus half of AB t squared. It doesn't equal to half of AB plus half of BA. That is where the little detail matters. Because a matrix, if you just multiply swap terms, AB doesn't necessarily equal to BA. So these two terms are not necessarily the same. So that's my point. The point to make this conclusion. Right? This two only equals if A times B equals B times A. Otherwise, you cannot directly add the matrix together. In here, you don't have the problem. In here, it's exactly the same. A is A. In here, you are adding the scalar. It's not the matrix. So that's fine. Anyhow, that's the fact about matrix computations that we need to be careful about. Here are the relevant how we can use these results from here. We talk about the general formula, the definition, how it actually looks like, this exponential function of a matrix. So it is this. So let's look at some of the typical structures for A. Let's see, if A is a diagonal, right? This is something that we love very much. Everything will be easy if A is diagonal. Because if A is diagonal, then A squared, if you multiply A with A, it's going to be diagonal. If you multiply A to the power of n, it's just the diagonal elements to the power of n. That's the convenience brought by the diagonal matrix. In the Taylor expansion, in the formula, you can see A times T is diagonal, I is diagonal. A squared times T squared is also diagonal. So all these are easy to compute. So here is the details. Identity is 1, 1, 1. AT is this matrix times T. Matrix times scalar is the scalar multiplying the individual elements. So it's lambda 1t, lambda 2t, lambda 3t. And A squared, T squared is also diagonal, right? So A squared is A times A is lambda 1, lambda 2, lambda 3. The first row of this product is lambda 1 times the first row plus 0 times the second row plus 0 times the third row. So the first row is lambda 1 squared, right? So it's lambda 1 squared here, and then multiply T squared and half of here. The second row, using the row interpretation. The second row of this product is 0 times the first row plus lambda 2 times the second row plus 0 times the third row. So it's lambda 2 squared times T squared and half of and 0.5. Same thing for the last row. So this is diagonal. All right? You can add these elements together and get 1 plus lambda 1t plus half of lambda 1 squared t squared, etc. And then we can immediately recognize this part is what? It's exactly the Taylor expansion of E lambda 1t, right? So that's E lambda 1t, E lambda 2t, and E lambda 3t. All right. So the important message here is that if A is diagonal, then the computation is very easy. It's just diagonal elements scaled, taking the power exponential function of the diagonal elements. Diagonal is one, we have one canonical realization for diagonal matrices A. The other canonical realization is the Jordan form that we mentioned in the last lecture. So the matrix looks like this. It's the next best thing for A matrix. It's not entirely diagonal, but it looks very much like it. Just a bunch of ones sitting in the off-diagonal terms. If you can't get diagonal, get Jordan form. It's also very nice. So let's see. If A is in Jordan form, how EAT looks like. So from here is we can do some decomposition. So it's relatively not straightforward. If you use if you use directly the Taylor expansion, if you use this directly, it's a little bit uneasy. Can you imagine? AT is easy, but when you compute A squared, then you have a lot of computations you need to be careful about, right? So if A times A, in this case, you can generate more complexity in the structure. So what we do is this. I know how to do diagonal, so I decompose A into a diagonal plus a matrix that looks like this. A lot of zeros inside, and then the non-zero elements are just 1. So then let's see what happens. Here, I'm defining this as lambda times I3. This is matrix N. So EAT is decomposed into lambda IT plus N times T. All right, so what did we talk about? EAT, EBT, and EA plus BT, right? It equals only if A times B equals B times A, and we'll use this here. Treat this as A, treat this as B. So A times B is lambda IT times NT. T is a scalar, so you can multiply to here. Identity matrix times N is still N. And then lambda is lambda, a scalar. So it's the same as B times A. You see, if you swap the order, then T is T. You can get it from here. Lambda is lambda. And then N times identity matrix is still N. For this case, we can use the formula. We can decompose this EAT into 2 terms. The first term is e to the power of A, and then the second term is e to the power of NT. Now, e to the power of the first term, this is the diagonal matrix, right? This is lambda, 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 T. And then it's going to equal to, we know how to do the diagonal, is E lambda T. To be more specific, I want to write it a little bit more carefully. So from here to here, you actually need to go to two steps. So it's E lambda T, lambda T, lambda T, 0, 0, 0. So it equals E lambda T, E lambda T, E lambda T. So diagonal exponential function of a diagonal matrix is taking exponential function for the diagonal elements. And then this one equals E lambda T times identity. So that's why the result here. So the only thing remaining is this one, ENT item. But that one turns out to be fine because it has the nice structure, a lot of zeros and 1 in the off-diagonal elements. Any questions? All right. We got the big steps cleared out. We want to compute a Jordan form, a non-diagonal form. Now we have go through the decomposition. So the only thing that we need to be careful is this one. This matrix is very interesting. So let's take a look. In the 2 by 2 case, it looks like this. So in the 2 by 2 case, N2, what will happen if you do N2 times N2? All right, so let's do row interpretation again. What is the first row of the result? What is this one? It's 0 times this row plus 1 times this row. So it's 0, 0. And then the second row is 0 times this row, 0 times this row, so it's 0, 0. So after you multiply this matrix by itself once, you already got 0. If you do 3 times, it's going to be 0. Right? Similarly, for this one, it's sort of like doing this. This off-diagonal 1 term, after you multiply once, it goes 1 line to the right. So it disappears. So if you shift this one item, one entry up to the northeast, then there's no more space. So it falls out of the 2 by 2 matrix. It becomes 0. All right? For this one, it's exactly the same thing. For this matrix, 3 by 3 case, you can see this interesting sort of the elements, non-zero elements sort of matches towards the top right until they disappear. So let's say 1, 1 here times itself. What is the first row again? It's going to be 0 times the first row plus 1 times the second row, right? So it's 0, 0, 1. And then the second row is 0 times the first row, 0 times the second row, 1 times the last row, 0, 0, 0. And then the last row is always 0. You see this off-diagonal element sort of matches to the northeast until it disappears. So this property is called nilpotent. This matrix is called a nilpotent matrix. Any matrix has this structure. A lot of zeros and then ones sitting in the off-diagonal side is a nilpotent matrix. Nil means 0, and then potent means you take the powers. All right? This is a nice matrix to conclude. So this matrix, after this one, for the 3 by 3 case, after you multiply itself, take the power to 3, it becomes 0. Power to the 4 is 0, etc., etc. So ENT is actually amazingly easy. So ENT is I plus NT plus half of n squared t squared, and then all the remaining terms are 0. Any questions? So just the 3 terms, it's easy to compute. I is 1, 1, 1. NT is 0, t, 0, 0, 0, t, 0, 0, 0. And half of NT is half of, we already talked about here. We computed n squared, right? So half of n squared t squared is going to be 0, 0, t squared, 0, 0, 0, 0, 0, 0. So you just add these entries together. You get 1 in the diagonal, t in the off diagonal, and then half of t squared in the top right. So nilpotent matrices, the exponential function is easy. So therefore, with this overall equation, EAT is going to be this whole thing multiplying in lambda t. Just so this time be now careful. This time you got a scalar times a matrix, right? So you need to multiply this scalar into all the elements of this matrix. So it's E lambda t, E lambda t, E lambda t, t, E lambda t, and t squared over 2 E lambda t. All right? So that's the Jordan form of a exponential function of a Jordan matrix. Any questions? So I will, yes?
So for, if you have an n by n matrix, then you just have to expand it to the like n minus 1 term and then add up all those.
Mm-hmm. Yeah, that's actually an exercise I think. Cool. All right. That, I would like to stop here about the new materials and then do two things. One is to go through one exercise, and another is to show you the MATLAB commands. This is one of the problems as an exercise. Spend some time on the problem statement. The key information for problem 1 is also written on the whiteboard. All right. You have taken some look, and let's work on this problem quickly. First is the transfer function. I will cover most of the questions here, but not all of them. So let's see, what is the transfer function for this one? You do z transform, assuming 0 initial conditions, then you get z squared yz minus z yz plus 0.25 yz equal to uz zuz plus 0.8 uz. So from here, you can get the transfer function of g, which is y of z over u of z. So it's going to be z plus 0.8 over z squared minus z plus 0.25. That's the transfer function. And then the next question is controllable canonical form. So this is, we have done one exercise at the beginning of the class. For this one, it's very similar. So for this one, the controllable canonical form is, all right, A should be equal to, take a look at, so it's 1, the easy terms first. 1, then this term, this is the term negative of A term here, and then negative 0.25. And B is controllable canonical form, so it's easy. So it's 0, 1. C is what? So I need to take a look at the coefficients on the top. 0.25 corresponds to 0.8, the position, so it's 0.8, and then 1. D is 0. That's the CCF. Observable canonical form is easy. So for this part, OCF still here. OCF is, you can write out the easy things first. So observable canonical form is 1, 0 for the C. And then in the A matrix, it's going to be 1, 0, and then 1, negative 0.25. All right? So it's sort of like this row flips up. And then B is 0.81. That's the observable canonical form. You can use the formulas. I want to talk about the diagonal, block diagram of this one. So we talked about the block diagram for continuous time systems. You have that in your lecture notes, right? So, and we also talked about how from there we can derive discrete time. It's just change S with Z, right? So is I will it is this slide. All right, so it's this slide. This is a third order system. You just need to make a second order case for this one. So you're going to get z. So at the beginning is always u, and then in the end is always y. So let's say yk, uk. It's like this is the last, this is corresponding to this one here. So it's going to be x1, this is the state, x1k. And then it goes through b0. So it goes through, what is our b0 here? This is b0, right? And then to y. So this is x1, this is x2k, right? So, and then from x2, there is a line to the output with b1 as a scalar. b1 is 1. Okay? And then there will be some feedback terms. So from x1, there is a feedback going to the first summing junction before u. And the scaling is what? It's A0. What is our A0 here? 0.25, right? And then the other term, from x2, there will be another line, which is A1. And in our case, A1 is minus 1, and then that's it. All right, so that's the block diagram. Now, let me quickly show you that this actually works, right? So I'm going to show you. I'm going to build this state space system in MATLAB, and then I'm going to transform it into transfer function, and then show you it is actually the case. So let's say I'm going to define the matrices first. So A matrix, the font is a little small, but trust me, I'm inputting 0, 1, negative 0.25, and then 1. And then for the B matrix, I'm putting in 0, 1, and C matrix, I'm putting in 0.8 and 1. D is 0. So these are the state space systems. So you can define a state space system by G equal to SS state space, A, B, C, D. All right? And then let's check. This state space actually has a transfer function over there. To get the transfer function from the state space, you can do this. You can obtain the numerator and denominator of this transfer function of the system by SS to TF, and then ABCD. All right. So for those of you who cannot see clearly, the MATLAB is generating the numerator of the transfer function has coefficients 0, 1.8, which is the coefficients on the top on the right over there. Denominator has coefficients 1, negative 1.25 is over there.